last video of part D, D.3, linear recurrence relations. So now we prove the Fibonacci formula. But still, if you look at the formula, although we prove it, but still we feel we have not got everything, because the reason you can prove it is because you know it's correct formula. You know the correct formula, then you can prove it. It is true. The question is, how do you get that formula, right? You cannot guess it. Think about, can anyone guess this formula? Nobody in the world can guess a formula like this. It's impossible. Okay? Yeah. So the only way to get this formula is derive it. Derive it from the recurrence relation. Yeah. So for this D.3, we will derive it. Yeah. We need to solve the recurrence relation problem. Actually, this recurrence relation, linear recurrence relation problem like this, you should learn in discrete math, math 3000. You should learn it. Yeah, but probably most of you, may not have good impression on this topic. Yes, probably almost forget big part of it. Yeah, but anyway, here I want to derive the whole method another time, but when I do it, I explain a lot of ideas, thinking, concepts, method, a lot of things we need to use to derive this formula. All right, so let me start. First, let me use the right terminology to describe recurrence equation. The complete name of it is second order linear homogeneous recurrence relation with constant coefficients. You can see the name is so long. First, second order. All right? Yeah. So it looks like we are working on a sub n equals a sub n minus 1 plus a sub n minus 2. Okay? All right. So the largest subscript n minus the smallest subscript equals 2. That 2 corresponds to second. Okay? So the second order linear homogeneous. Let me explain the linear. Next, linear. Linear, you know the meaning of linear, right? No square, no other. So linear we mean, so the linear term of x, that is x to the first power. That's linear, right? So you can see the variable term, the exponent, all linear. First power. Okay? Yeah. So that's the linear. Homogeneous. Homogeneous means there is no constant part. Okay? Yeah, because so the variable part, variable. After the variable, if you put a constant there, c, then it's not homogeneous. If c not equal to 0, then it is not homogeneous. The constant term is gone. No constant term, then we call it homogeneous. This homogeneous property, so usually we know the homogeneous equation relatively easier to solve than the non-homogeneous equation. So homogeneous property is a good thing for us to solve the problem. Good property. Yeah. All right, so homogeneous. Then recurrence relation with constant coefficient. Yeah, the coefficient of A sub n, so coefficient, these constant coefficient. You do not have the variable part in it. If you have variable part, then it is very complicated. Yeah. So here you can see with this long name, we get a relatively easier problem to solve. Relatively easier problem to solve. All right, so with all these things, yeah, so that's the general format of this type of recurrence relation. And here, B should not be 0. Otherwise, it won't be the second order. It will be first order. If B equals 0, we get a first order linear homogeneous recurrence relation with constant coefficients. All right. Then for our Fibonacci numbers, A and B both equal to 1, the special case. Yeah. So we just need to solve this recurrence relation. Yeah. Next, let's look at solving Fibonacci recurrence relation, the general method. We are working here. Yeah. Take a special view. So here, the view, the understanding of this equation, the structure, is critical. So let us try to understand that part. All right. Consider a sequence A sub k. Yeah. The sequence, the Fibonacci sequence, A sub k. Now we need to imagine what possible structure this sequence can take. That is important. We like to put a special structure on the sequence so that we can take advantage of that structure. Yeah. So what's that? Yeah. Here we can make a guess, but you have to make a smart guess. You have to make a reasonable guess. Your guess cannot come from nowhere. Your guess has to come from something related to this question. So that is important. Okay? All right. So how do you get that kind of guess, the structure guess? Yeah. Here, I may, bring up our old example, the Tower of Hanoi problem. Remember, we have a simple recurrence relation there. In that problem, let me recall. So that equation a little bit quickly, connect to this one. That recurrence relation, the original one, Cn equals 2Cn minus 1 plus 1, right? That's the original recurrence relation. But that one, non-homogeneous, plus 1, constant term, not equal to 0, non-homogeneous. Then remember, after we add 1 to both sides, then we create a new notation, d sub n. Yeah. So then we get d sub n equals 2 times d sub n minus 1. Then we get homogeneous equation. First order linear homogeneous equation. Then we think about it. What is the solution of that? The solution is 2 to the nth power, right? Remember? Solution 2 to the nth power. Good. This one gives us the structure of a recurrence relation. Although it's a first order, but it gives us, this is the structure we should consider. because our guess should come from somewhere, some related thing, but not nowhere, right? Yeah. With this connection, can we put the structure t to the kth power? Yeah, 2 to the kth, right? 2 to the n, t to the kth. This structure we can try. Can we try that? Yes, that's something related. All right, yeah. So this we call geometric sequence. This is a geometric sequence. Here we try to, test if the geometric sequence can satisfy this recurrence relation. Yeah. Try something related. Yeah. All right. Yeah. When we try, we should ignore the initial condition first. Yeah. Later we will fix it, but at the beginning, at this point, let us ignore it so that we can, do it faster, easier. Yeah. All right. So let's work on it. So let's plug into our recurrence equation. We get this equation. It becomes a simple equation with one variable t. Yeah. Then after we simplify it, we get t squared equals t plus 1. It's a quadratic equation, and we know there are two solutions. We can write them out using the quadratic formula, the t1 and the t2. Here you may connect this equation to the one when we derive that golden ratio, right? Golden ratio. You may connect to that. Yeah, exactly the same quadratic equation. But here, when we consider this equation, we do not have the background of that, the one we use for the golden ratio. We don't have the background of that. When we don't have the background, so that means T1 solution, T2 solution, both could be considered as valid solutions for the original equation. We should not drop anyone. In our golden ratio one, we know the ratio of two line segments cannot be negative, right? Cannot be negative, so we drop it, the negative solution. But here we cannot drop the negative solution. Here there is no reason to drop the negative solution because here our t does not represent the ratio of two line segments. We don't have that. Yeah. So we keep both solutions. All right. So let's move to the next page. We try to get to our final solution. Closer and closer. Yeah. All right, so let's start. Yeah. So two different solutions to start with our continuation of the deduction. Yeah. First, T1 satisfy what? Satisfy the original recurrence relation, right? T1 satisfy that, right? Yeah. So if we make an equals t to the nth power, can we get this equation? That must be correct, right? No problem. It is correct. Okay? T2, if we T1, let me use T1. If we use an equals t2 to the nth power, we can get the second identity. Both correct, right? Both correct. Yeah. Now we can treat. We have two special solutions of the original recurrence rate. They are two special solutions. They are not general solutions, right? There are two special solutions. And also, They are not integer solutions. They are not integer solutions. We want to have integer solution. Our final solution, Fibonacci numbers, they must be integer solutions. But here, none of the two special solutions is the integer solution. It's okay. We don't worry, because they are the intermediate solutions. They are not our final solutions. So we don't worry about, that part. Yeah. All right, so let's get to the next step. These two special solutions do not satisfy the initial condition, right? Yeah, definitely not, right? Yeah. So it's okay. It's not. We will fix it. We will fix it. The question is, how do we fix it? Yeah. Next, the question. How to use two special solutions without initial condition to get a new solution with the initial condition. That is a natural step forward. We need to get a new solution. Those two special solutions, none of them satisfies our initial condition. But we do not give up. We try to modify those two solutions to get a new solution, and we hope the new solution satisfies the initial condition. So that's the natural logic. All right. Is there a special way to combine two solutions? We want to combine two solutions, but we need some special way to combine them, right? That combination, that special combination method, it is important. Yeah. So we need to look at that. Yeah. All right, so now let's work on the combination part. Yeah. Linear combination of two variables, x and y. Yeah. How do we combine two variables to get a new expression? And we use linear combination. This concept, there is a concept called a linear combination. Linear recurrence relation. So that's the reason we need to use the linear combination. We don't want to use the non-linear combination. We want to use the linear combination, preserving the linear structure. Otherwise, we may break the linear structure. We don't want to break it, right? But what is the linear combination? That concept. Yeah. Here, ax plus by, we call the linear combination of two variable x and y. Here, capital A and capital B, both two constant to be determined later. Yeah. Here, we just use general constants, ax plus by. That whole thing we call a linear combination of x and y. All right, so here, let us use this linear combination for our two special solutions. Yeah. All right, how do we use that linear combination? Linearity property. Yeah. So our solution has the linearity property. Yeah. All right. Yeah. Okay. Solution 1 satisfies the recurrence relation. Solution 2 also satisfies the recurrence relation. Then, because that is a linear recurrence relation, so it has the linearity property. So then we do the linear combination of the two special solutions. It should also satisfy the linear recurrence relation. That's the main property. Yeah. All right. So the new form of the solution, A times the first solution plus B times the second solution. That's our new general form of the solution. A, B could be any constants. A, B to be determined based on the initial condition. Yeah. Next, how to determine these two constants. Okay. We have some information. Yeah. Two initial values can be used to determine a constant and a B constant. All right. So now the last step, we just fix those two constants. Then we find a solution. Yeah. So let's do that step. All right. The goal, determine the coefficients A and B such that initial condition is satisfied. All right. So let's do the work. When n equals 0, let's plug in n equal to 0 in our general solution format. Yeah. So we get A0 equals this expression, and then we know A0 equals 0 value. So we simplify the parentheses. 0th power, non-zero number to the 0th power, that's 1. So A plus B equals 0. Then B equals negative A. Yeah. When n equals 1, so you plug in, so you have this expression. We know B equals minus A, right? So we can replace B by minus A. Then we factor A out. Yeah, we know that A1 equals 1. Yeah, but the expression, we can simplify it first. So the parentheses, after we combine these two terms, after simplification, we get A times root 5 equals 1. So that means A equals 1 over root 5. Then B equals negative 1 over root 5. We plug in these two coefficients back to our general formula expression. Here we replace that 1 plus root 5 over 2. The whole explicit fraction using our golden ratio phi, 1 minus root 5 over 2 could be represented as negative 1 over phi. Then we go back to our original form. So we get 1 over root 5 parentheses phi to the n minus negative 1 to the nth over phi to the n. That's the correct formula for the Fibonacci numbers. That's the whole derivation procedure. Okay? So we apply the mathematical tool rigorously to find a solution. That's not a guess. That is a, rigorous solution. No. Well, because nobody can really guess that solution. So we have to use this way to derive it. Yeah. All right. So try to understand the whole derivation procedure, and then later we need to do some calculation on it. Yeah. All right. So here I finish all 3 videos of part D, and we complete the whole lecture today. Yeah. All right.